So, electrodynamics. Something moves and you get electricity, or electricity flows and you get movement. Okay. Electrodynamics. Okay, so if electricity goes in, what kind of apparatus do we have? If we pump electricity in, what are we getting? We made one last time I saw you. What did we make? A motor. And to make the motor we needed a big fat battery. So we needed a big battery. I've got the battery somewhere. Did I need big magnets? I used, what are those magnets called? Neodymium magnets. So I need a big current, big magnets, and then we got a motor going. Some of you saw it, unfortunately some didn't. But you'll have to believe those who saw it. Okay, so electricity in, we have a motor. And what comes out? What comes out? Mechanical energy. In the form of PK, kinetic energy. Right. Now here I've got something. What type of energy am I putting in? Mechanical. I am putting in mechanical in, and I'm getting out electrical. So what is this thing called? It's a generator. So I took this apart, although you can't see it. It's got a permanent magnet in the center that spins. It spins a magnet in a coil, past a coil, and generates this electricity enough to light the LED. It's producing, I think, alternating current. And the LED doesn't mind alternating current because it will work with alternating or direct. It will just stop the current going backwards. That's what LEDs do. Okay, so that's quite cute. Anyone know where we find generators commonly?
Hospitals.
Hospitals, right? So you don't want to be there with open heart surgery and poof, ESCOM decides to have the guy who's moving the magnet inside the coil get tired and fall asleep. And then your heart-lung machine just dies. So in hospitals, anywhere else? Do any of you have a generator at home? No? Okay. What else can we say? I've got a generator at home. I made one. I took an exercise bike. You know, it's got a spinning wheel. You know the spinning wheel on an exercise bike? You pedal it, the wheel goes. I took a car alternator, and as the wheel with the rubber turns, it turns the alternator. So that's in your car to charge your battery. So then the alternator got going. I had a little battery there, and I generate my own electricity. And then you get a thing called an inverter. I've got a video of it if you want to see me sitting on my exercise bike. Then the inverter turns the 12 volts into 220 volts. Oh, I should have asked you that question. Do you all know that out of the mains comes? 220. 220. At what number of hertz? At exactly 50 hertz. So the guy at ESCOM is doing this 50 times a second to keep your 50 hertz. But anyway, so I sit and I pedal. The inverter turns it into 220. The 220 powers my TV. As long as I can keep pedaling, the TV keeps working. That's what I've got at home. So if you get lazy, you can't watch TV. That's. So I try to sell this thing. I'm tired now of peddling. No one wants to buy it. Any of you want to buy it? I'll give you a bargain, 800 rand. Because those alternators in the cars are quite expensive. Okay. Maybe I'll have a special deal for you. Okay, now, this is a magnet. What are those things that stick out of a magnet? What do these fingers represent? Here's my magnet. Out of the tip comes things that spread like that. What are these called? They are called magnetic field lines or flux lines. And if that's your magnet, they go from north to south or south to north? North to south. Have you seen that pattern before? Okay. North to south. Now, last time I got a bit of a rise out of you when I asked you for Faraday's law. And it seemed like you'd seen it last year, right? But you didn't seem to know what it meant. Any of you got a better idea of Faraday's law now that we spent 5 minutes on it? Who'd like to tell me what Faraday's law is about? Okay, I'll give you a hint. It starts with that. What does that stand for? Sorry? EMF. Now, what can you tell me about that EMF? Is it induced or is it just any old voltage? That means that you're generating this voltage, right? So this is the induced EMF. Depends on 4 things. What are they? How do you get a strong generator? Okay, lovely. Number of turns. You see, God is not going to give us something for nothing. If you want lots of voltage, you've got to use lots of copper, lots of turns. What else? The size of the magnet. Okay. Now there's 2 things about that magnet. Here's your magnet. Do you see that if you have a bigger magnet, right, or 2 magnets, you're going to get twice as much field lines. Does that make sense? So it depends on a thing called phi, but phi has got A and B parts to it. A stands for area. B stands for the strength or the flux, number of flux lines. Okay, so just have a look here. If I add another magnet, am I adding more area of magnetic field? Does my A become 3A from 1? So 1A, 2A, 3 areas. B stands for the strength of your magnet. If I use neodymiums, what am I going to do to the field lines, the flux lines? What will happen to their density? Will it increase or decrease? We're going to have more field lines. So that is the B, the number of field lines. So you could imagine, it's like having an old toothbrush. Here's your toothbrush. Your toothbrush could have a big area, but it could have 2 little bristles. It's possible, right? So of the A and B, what would those 2 little bristles be referring to? B, flux number or the bristles. Just think of it, B for bristles. You might have a nice big area for your toothbrush, but it's no use if it's only got a few bristles. Make sense? Putting it all together, there's one last thing. So it depends on the number, A, the area, B, the number of bristles, and there's another fourth thing that we have to have for a good generator. Right. What happens the faster we move those flux lines? The bigger your voltage. Because you're putting in more energy, could you expect to get less voltage? No. If you could just lie the magnet inside the coil and go to sleep, you'd be getting something for nothing. Nature doesn't like that. You're not going to pass your matric if you don't do something. So the last thing is the change of time, delta T. Now actually, A and B, which is called delta phi, which is also delta A and B. You've got to have changing flux lines to get a voltage. Changing flux lines with changing time, because you've got to get the flux lines to cut the coil. Here's flux lines. They're coming, they're about to cut our wire, but they're not moving. So then you're not getting a change. You're not getting flux lines cut the wire, and therefore you're not going to get a voltage. Now if you get tons of flux lines and they cut the wire, you get a big voltage. All happy. So that's why we have delta. And then what else does Faraday's formula have that comes? We're missing something here. EMF equals number phi over delta T. There's a negative. I looked it up. I was interested enough to wonder why it's negative. And it's this. The induced EMF opposes the flux lines. It opposes the flux lines. And that's why it's negative. Now, you know nothing, you have no clue what I just said. And that's not your fault. What do I mean by opposes the flux lines? It wants to cancel out the flux lines. And now we're going on to motors and generators. Now, this is drawing it from above. We gave you a notation that looks like this. What did we put there and here? What does that stand for? The wire is coming, the current is coming out towards you or away from you? Remember, if you see a tip of the arrow, you see the point of the arrow. So this is the arrow tip. And the current is coming out of the board. It's coming this way. And if you see that, that's the fletchings of an arrow or the feathers of an arrow. It means the current on this side is going into the board. Okay. Now, is this a motor or a generator? Well, we don't know yet, do we? What don't we know? If we are giving it this current, what do we need to give it the current? We must have, what are these things? Brushes. And if the brushes are attached to a battery, here's my battery, and I'm putting in electricity, then that must be a motor. Now just look at that. That's conventional current. Conventional current goes from, come in, from, sure. Do you guys know which side of this battery, left or right, will be the long stroke? Think about it. So the current is coming like this, and it's going that way. Now, which side of the battery should be the long stroke? Is the long stroke, which side is positive, the long or the short? Okay, so we established that is positive, that is negative. The short one is negative. Now, which one of those is going to be, which way around must my battery be to get the current to flow like that? Anyone got an idea? Okay, so let's work it out. Conventional current flows from positive to negative or negative to positive. Conventional current flows from positive to negative. So what must this side be?
Positive.
Do you see that this must be positive and that side must be negative? Now let's follow the current. The current goes from positive, goes through the brushes, and now it's going that correct way. Coming back to the negative side. Anyone would like me to explain that again? So conventional current goes from positive to negative. Okay. Now, our cheap and dirty way of drawing all that is just to draw this. Isn't that a lot nicer? If you were setting this exam, you would choose this way every time, because the other was a lot of drawing. Okay. So is this a motor or is this a generator? Had a battery coming in. It's got a battery, so what goes in? Electrical energy. So this must be a motor. So now my question is, which direction does your motor turn? Clockwise or anti-clockwise? What are you going to reach for? To find out which way your motor turns, what are you going to reach for? Which hand? Your left hand. Okay, now to help you remember, you're going to do this. That's the current. Just do it, everybody. Shock yourself. That's the current. Do this. This is the field. You're pulling it apart, the field lines. And do this. This is your thumb, is the direction it thrusts. Now, who can work out for me which direction this is going to go in? Let's see everybody work it out, and then we'll take a vote. Science is democratic, okay? So everybody use your left hand and work out which direction this motor is going to turn. Let's see. Let me hide it from you. Okay, that was easy enough. Okay, who says it is anti-clockwise? Who says it is clockwise? 1, 2, 3, 4, 5, 6, and the rest. You're not voting. You're not exercising your democratic right. And the 6 are right. So let's just figure out why. We take this field line, we point it from north to south. So that finger is north to south. This current finger is coming towards me, so the thrust must be up. And if I worked out the same for that one, the thrust would be down. And that's a common question in the exam. Can you get it wrong? Well, I suppose anything's possible, but it's pretty easy, isn't it? Do you agree? Pretty easy? Okay. Lovely. Now, this is why I wanted to tell you. Did you know that as this turns, it now becomes a generator? because now it's got mechanical energy. Do you know that as it starts to generate, it actually produces an induced current in the reverse direction? Did you know that? I'm going to teach you something. Did you know that it's actually, as it becomes, as the motor starts to turn, it generates a reverse current as a generator? Who's hearing this for the first time? I'm sure most people. Right, yeah. So this motor is a generator. Because the moment it's turning, irrespective of what the source is, it's now got mechanical energy and it's inducing a reverse current. And that is where you get the negative from this side. Because it's opposing the original current and the original field. Now let's try not to confuse you. Now let's suppose we have a generator. And they draw you a generator that looks like, let's do this. What do you want here? Let's put south, let's put north here. Do you want a dot or a cross there? Okay, across there, dot, don't say I never give you a choice. Now let's say this is a generator. Okay. I said a generator and a motor are the same thing. A motor, when it turns, becomes a generator. A motor is always a generator. At the same time as a motor is a generator. As soon as a motor starts to turn, it produces a reverse current that opposes the original current. So in a motor, you've got two currents opposing each other. Sounds weird, right? Now, I'm going to not confuse you. Take your right hand. Put your three fingers like this. This is still your bzzz current. This is still your field. This is still your thrust. With a generator, what comes in? Thrust. Okay. Thrust comes in. So, I guess what I have to do is I can't give you those yet. That's right, because of the generator. Which way do you want this to turn? Clockwise or anti-clockwise? Okay, anti-clockwise. Now, using your right hand generator rule, Fleming's right hand generator rule, find out the direction of those currents. So what do I do?